Borshas conjecture, namely, presume that if the minimum degree is k minus over k times n, then it follows and G contains a k minus 1 power, so the Hamilton cycle. Now you notice that these numbers are exactly the same as in the discrete case, yes, in the triangle cover or in the complete k-graphs cover, yes? But nevertheless, the same numbers, and of course then, if the conjecture is true, then it is tight, because it was already tight in the case in the discrete case. But here it is continuous, and so it's a much richer structure. Nevertheless, the threshold is the same, 2/3 k minus 1 over k times n. And then so actually this is somewhat surprising. Then the threshold is the same even if we are looking for a much more complex structure. Okay, so the minimum is k minus 1 over n. And then the conjecture then G contains k minus 1 power Hamilton cycle. And then around 2000 with Comro Sarkozy, we proved both conjectures, but only for very large n, because then the proof contains the regularity lemma and the blow-up lemma, and inheritively the n involved here should have been large. Now, right now we have a new proof. It's one of my students, Asif Yamsher, which doesn't have the regularity lemma, and then it actually has what is the main thing about the whole, in that it's a new kind of connecting lemma, and I will make or will not explain what it is. But that actually has already been used in many other papers, because this is pretty powerful, quite complicated, and it's much more complicated than the whole connecting lemmas, because obviously you have to connect here things. But on the other hand, it is very flexible, so you can use it for hypergraphs and so on. And this is nothing else, just induction, and then eventually everything will boil down just to check whether in a graph every 2 points is the graph is connected graph, and it's easy to check whether the graph is connected graph. So, and actually this really reduces to the very elementary fact. Okay. Now, it's not a joke, but there is this so-called race. It's not really a race, but people really want to decrease and to as small as possible, and of course eventually do it for every Borshas conjecture. For k this is almost hopeless. And then Kirstead, Tigacio and Zhao proved that if n is at least 300 times 10 to the 6, then your graph under this condition contains Hamiltonian cycle. But look, why is this number here? I have no idea. But then, after some investigation, I found the reason, because actually, more or less, this is the population of the people in US. It's about 300 million, yes? No, and then I asked the author, this one is American, obviously Italian, and so that was the main reason. But then, of course, there are smaller countries, so then now with Bela Chava and other two of my students, we proved, you see here there is a question mark, that n is less than 1000. So you really don't have to always concentrate on US, you can do something else. So n is less than 1000, but the proof has to be checked, because we just wrote it up. But the point is that I am not sure whether the proof is correct or not. But most probably is correct. But I have to emphasize, but to some extent it is worthless, because even if it is 1000, you cannot check with the computer that is contains, and that is just too much. 2 to the 1000, all the cases you have to check that there is no computer. But if you reduce it to 100, then now the computer could check. And now it is very fashionable to prove something with the help of the computer. Some theories in it, and then computer comes and takes over. But we are not there yet. Now the next one is packing trees into a graph. So what is packing? That you are given two objects, a graph which is a host graph and another graph which is a guess graph. And then the host graph and the guess graph size is the same, namely they have exactly the same number of vertices. Because otherwise if the guess graph is smaller, has a smaller number of vertices than the host graph, then obviously your task is easier. But now we want them exactly the same. So from now on we will assume that the host graph and the guess graph has exactly the same number of vertices. And now definitions very fast. Delta, so we have a tree, and then delta t is the maximum degree as opposed to the minimum degree. And now no other notations we need. Then Golobash in the 80s conjecture, it's almost always the same ANOVA 2 appears here in these games. Then if the minimum degree is 1 plus epsilon, notice that there is this extra epsilon times ANOVA 2, and the tree is somewhat restricted. The maximum degree is C, then N is large enough, then G contains a T. Okay, so that was Golobash's conjecture, and then he solved it with Komlos and Sarkozy. But you have to investigate a little bit more. Then what can we say about, well, it is needed, epsilon is needed. Well, maybe then first maybe better if we concentrate on T. So is it needed, then we will have the restriction that the maximum degree is less than a constant. Not too many trees have these properties, yes? The maximum degree usually is much bigger than D. So then first we investigated the following question, and still we have the host degree has a degree 1 plus epsilon over n over 2, but the tree now doesn't have to, the maximum degree of tree doesn't have to be less than C, but rather it is it can be much bigger, and much bigger means that maybe the next, I hope it will be 7, yes, then the degree has to be less than, here PowerPoint, less than 1 over 100. This is an artificial number here. Actually, it's 1/2, you can prove it, but then your proof will be much more complicated. It's not worth to determine here the best constant. But you see, the maximum degree, so if the tree has maximum degree less than 1 over 100 times n over log n, then delta G and the delta, so then still the previous, I will not go to this one at the moment, then the minimum degree is 1 plus epsilon times n over 2 of the host graph, then T is contained in the host graph. But look what happens. If the minimum degree of the tree is bigger than 2 times n over log n, like here you can see, then the root has a degree 1/2 times log n, then of course all these points have degree 2n over log n, then this T cannot be embedded in a graph even if the minimum degree is 9 over 10 times n, much more than 1/2 times n. And the reason is that if you just take a random graph so that it contains 1/10% of all of the edges, then it's very easy to check that this is not contained, even if I forget about the root. So you see 2n over log n and n over log n almost is the same number, except here constant. If it is 2, then you cannot do the business. But if it is 1 over 100, then you cannot do the business, you cannot. So actually, in that sense, it is very, very, very tight result. And then, now, what we proved with Viracha, what was the next question, whether we can read off the epsilon. And yes, we can read off the epsilon, namely, if the minimum degree is bigger than n over 2, of course you cannot get rid of n over 2, because already at the 1 factor we have this threshold, yes, n over 2. So n over 2 plus delta t times log n, then you see the error is proportional to the maximum degree times log n. And if the maximum degree is this, then of course this is n, you cannot say anything more. So that n is tight, and of course the maximum degree is constant. Then also I should go back. Yes, that this graph there shows that also this is time. So you cannot do, if the minimum degree, if the maximum degree is less than c, then you have exactly the same result. But this example, I will not prove it, show them the result is time. So you cannot, the error term has to be of order log n. But what we cannot, because it involves a lot of probability theory, we cannot prove anything in between. The two extreme cases, when it is big or it is small. But maybe let it be square root 10. The maximum degree of t is square root 10, then we cannot prove anything. Most probably this error term will be slightly smaller. But actually, very strangely, the extremal case causes the problem. What is an extremal case, I will not explain now, it will come up later. But nevertheless, we don't know what is in between. But still, good error term, but we suspect that this error term in between will be smaller. Okay, now this this paper, this is not that extremely complicated. This is about 50 pages. But again, I have to admit that first when we submitted it, it was refused, and I could tell you which journal we sent, and the editor of that journal is a very tough guy, though my friend. So actually it showed that it's not enough to have a friend in a journal in the editorial board, but you also have to submit a paper without error and saying something. So, but now they accepted, so it